The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I guess last time on Friday we went over the first half of the class very quickly. And so today we're going to go over the second half of the class very quickly. Okay, so that was stuff about double and triple integrals and vector calculus in the plane and in space. So as usual, what's on the final, basically what was on the R test, exactly the same stuff. Well, not the same problems, unfortunately, but so the first thing we learned about was double integrals in the plane and how to set up the bounds and how to evaluate them. Okay, so just to remind you quickly, the important thing with iterated integrals, so when you integrate a function f of xy, say dy dx, for example, is that you have to draw a picture of a region. Unless it's completely obvious, you should really draw some picture of the domain of integration. And once you have that picture, you can use it to find the bounds. So remember, the general method is that we first look at the inner integral. So here, integral of f dy. And in this inner integral, the outer variable here, x, is fixed. So that means we are slicing our region by a vertical line corresponding to a fixed value of x. So we fix a value of x. And what we have to find out is the bounds for y. So the value of y at this point, the value of y at that point. Let me call that y sub bottom of x. In general, it depends on x. And this one will be y at the top, and it also depends on x. And then the bounds for y would be like this. And then when you look at the outer bound, things are different, because there you expect to have just numbers, no longer functions of anything. And what you do is you look at the shadow of your region. So what do I mean by shadow? You just project to the x-axis. Okay, so if you project to the x-axis, your region will look like this. So its shadow is going to be this interval from some minimum value of x to some maximum value of x. And that will give us the bounds for the outer integral. And then to evaluate, we evaluate the usual way. So speaking of evaluation, what do you need to know for the final? Well, essentially the same kind of evaluation techniques that we were supposed to know for the R tests. That means the usual functions, substitutions, basic trig, stuff like that. Okay? Well, I don't expect that you would need integration by parts, although I still hope that some of you remember it from single variable calculus. If there's a need to integrate some big power of cosine or of sine, then the formula will be given to you the way it's in the notes. Okay? And of course, we know also how to set up these integrals in polar coordinates. And then the area element becomes r dr d theta. And because you integrate first over r, well, first of all, you should remember, the polar coordinate formulas, namely x equals r cosine theta and y equals r sine theta. And second, you should remember that what we do when we have our region is for a fixed value of theta, we look for the bounds for r just like before. So the way we're slicing the region is now we're actually shooting rays straight from the origin, and in a given direction, we're asking ourselves, how far does my region go? So you have to find a bound, you have to find whatever the value of r will be out here as a function of theta. And ways to do that can be geometric, or that can be by starting from the xy equation of whatever curve you have, and then expressing it in terms of r and theta and solving for r. So for example, just to illustrate it, we've seen, one of our classics has been the circle of radius 1 centered at 1, 0. So this guy, you have two different ways of getting its polar coordinates equation. One is to argue geometrically that you have a right angle in here, and this length is 2, this angle is theta, this length is r, so the polar equation is r equals 2 cosine theta. The other way to do it, if somehow you're missing the geometric trick, is to start from the xy equation. What's the xy equation of this guy? Well, it's x minus 1 squared plus y squared equals 1. So if you expand that, you'll get x squared minus 2x plus 1 plus y squared equals 1. The 1's simplify. X squared plus y squared becomes r squared minus 2x becomes r cosine theta equals 0. That gives you, when you simplify by r equals 2 cosine theta. Two ways to get the same polar equation. Okay? I should say this is an example in case you were wondering what I was doing. Okay. So we've also actually seen how to change variables to more complicated coordinate systems. Let's say UV coordinates, but of course you can call them whatever you want. So the main thing to remember is that you have to look for the Jacobian, which will give you the conversion ratio between dx dy and du dv. So for example, if you know u and v as functions of x and y, then you will write du dv equals absolute value of the Jacobian partial uv over partial xy times dx dy. Or if it's easier for you, you can do the Jacobian the other way around. And this Jacobian, remember, is the determinant of a 2x2 matrix that you obtain by putting the partial derivatives of u and v with respect to x and y. So then, when we have that, we can change the integrand f of xy into something involving u and v, possibly. And then we have to find the bounds. And to find the bounds, perhaps the easiest is to draw a picture of a region in UV coordinates. So, maybe you have some picture in the xy plane that might actually be really hard to draw. And maybe in terms of u and v, the picture will become much simpler. It might just become a rectangle. Of course, if you see immediately what the bounds are in terms of u and v, and they turn out to be very easy, then maybe you don't even have to draw this picture. But if it's not completely obvious, then that might be a helpful way of figuring out what the bounds will be when you switch from xy to uv. Okay, so we've seen some problems like that, and there's more in the notes in case you need more. Questions? Yes? Well, that's the second time you ask for something real quick in these review sessions. You're in a hurry. Take your time. Take your time. Okay. So partial uv over partial xy, that's just going to be the determinant of u sub x, u sub y, v sub x, v sub y. That's the definition. Okay? That's pretty direct. Okay, and of course, a general common sense thing that applies to actually all the integrals that we are going to see. There's two things in an integral. One is whatever you integrate. It's called the integrand. It could be a function here. It's a vector field in some of the flux things and so on. And there's another thing which is the region over which you integrate. Okay, and the two have strictly nothing to do with each other. So, when you're given a piece of data in the statement of a problem, you have to figure out whether that's part of a function to be integrated or whether that's part of the region of integration. If it's the region of integration, then it will go into the bounds of the integral and maybe in the choice of the coordinate system that you will use for integrating. While the function that you're integrating goes, before the dx dy and not into the bounds or anything like that. I know it sounds kind of silly, but that's, it's a good safety check. Ask yourselves when you have a piece of data, where in my formula should this go? Yes?
Going back to the top, with the double integral with the integral type two dimensions.
Yeah, so in case you want the bounds for this region in polar coordinates, indeed, it would be double integral. So r, for a fixed theta, r goes from 0 to whatever it is on that curve. So that would be 0 to 2 cosine theta of whatever the function is, r d theta. And the bounds on theta would be from negative pi over 2 to pi over 2. Okay? We've seen that one several times, so hopefully by now it's clearer. Okay, let me move on a bit because we have a lot of other kinds of integrals to see. So another kinds of integrals we've seen are triple integrals. And I'm putting them here. I mean, I'm not doing things in the order that we did them in the class, just so that, you can see parallels between stuff in the plane and in space. So when we do triple integrals in space, well, it's the same kind of story, except now we have, of course, more coordinate systems. We have rectangular coordinates. We have cylindrical coordinates. And we have spherical coordinates. And really, cylindrical coordinates only mean that we are, instead of x, y, and z, we are replacing x and y by the polar coordinates in the xy plane, so the angle theta and the distance r. So r is somehow the distance from the z-axis, and z is the height. Okay, so usually you don't have to choose between rectangular and cylindrical until somewhat late in the process, especially if you integrate first over z, because then the choice will come up mostly when you try to figure out what are the bounds for the shadow of your region. I mean, the z part looks exactly the same in rectangular and in cylindrical. Spherical is, on the other hand, a little bit more annoying because it looks quite different. But you should think of it as doing polar coordinates not only in the horizontal direction, but also in the vertical direction at the same time. So you have this angle phi that measures the angle down from the positive z-axis. And you have rho, which is the distance from the origin. And see, if I project to the z-axis, so r becomes rho sine phi, and z becomes rho cosine phi. So I hope that you all know these two formulas, but if you ever have, a small, somehow, memory lapse during the final, then you should consider drawing this kind of picture because it will it will let you check very quickly which one is sine, which one is cosine. Now, of course, we have to have formulas for dv in all these coordinate systems. So here, for example, that might be dz r dr d theta, or r dr d theta dz, or anything like that. Here, that might be rho squared sine phi times d rho d phi d theta. And the general method for setting up bounds is pretty much the same as in the plane, just there's one more step. So if you're doing rectangular or cylindrical coordinates with z first, for example, that's the most common. Well, if you do z first, then you have to actually start by figuring out, for a given value of x and y, or r and theta, where, what is the portion of the vertical line above xy that lies within my region. So that will go from z on the bottom of the surface, on the bottom of my solid, which depends on x and y, to z at the top of my solid, which also usually will depend on x and y. And so that will give me the bounds for dz, and then I will be left with the shadow of my region in the xy plane, And that one I will set up like a double integral over there. Okay? Strictly speaking, if you're curious, we could also change to weird coordinate systems using Jacobians with 3 variables at the same time. But we haven't seen that, so it won't be on the final. But it would work just the same way, just with more pictures to draw. And in fact, I just wanted to say, this rho squared sine phi, it's actually the Jacobian for the change of variables from rectangular to spherical coordinates. Okay, let's not think too much about that. So applications. Well, we've seen how to use double or triple integrals to find the area or the volume of a piece of a plane or a piece of space, and find also the mass. So remember, area is just double integral of 1 dA. Volume is triple integral of 1 dV. Sometimes, if it's the volume between the xy plane and the graph of some function, you can just set it up directly as a double integral. But there's no harm in doing it as a triple integral if you feel better about that. And mass will be, well, double or triple integral, depending on how many dimensions you have, of whatever density function you have, dA or dV. Okay. Then there's how to find the average value of some function. And so the unweighted average, well, let me do the 3-dimensional case, okay? You'll just replace volume by area and dV by dA and so on, if need be. So that would be 1 over volume of a solid times the triple integral of f dV, or if it's a weighted average, 1 over mass times the triple integral of a function times density times dV. Okay, so if you don't have a density, or if the density is constant, then that reduces to that one. Others we've seen, well, so in particular we've seen the notion of center of mass. So the center of mass is just given by taking the average values of the coordinates, x bar, y bar, x bar, y bar, z bar. So it's just this formula, but taking x, y, or z as the function. There's moments of inertia. For example, the moment of inertia about the z-axis is the triple integral of x squared plus y squared density dV. Or if you have just a 2-dimensional object, then it's the same formula, but of course with dA. And then we call that the polar moment of inertia because we thought of it as rotating the plane about the origin. But the origin is just where the z-axis hits the xy plane, so it's really the same thing. And we've also seen gravitational attraction in space. And I'll let you look at your notes for that. It's just one formula to remember. Okay. Questions about iterated integrals, things like that? Yes? So what I mean, so the formula that you should know about gravitational attraction is that if you have a point mass at the origin and you have some solid centered on the z-axis that's attracting it, then the force will be given by g times the mass times the triple integral of density times cosine phi over rho squared times dV. And of course, you will actually do that in spherical coordinates because it's easier that way. Okay, that's the formula I have in mind. But see, all these formulas just give you, examples of things to integrate. And how to set up the bounds and so on does not depend on what you're actually integrating. It's done always using the same methods. Okay, let's move on. Work and line integrals. So we've seen how to do that in the plane and in space, and it looks very similar somehow. So remember, you have to know how to set up and evaluate a line integral of this form. And concretely what you do, so if you're in space, well, let me do it in the plane this time. If you're in the plane, you have two components, and then this becomes the line integral of m dx plus n dy. If you have a space curve, then you will have a third component, and you will add that guy times dz. Okay. Now, how do we evaluate that? Well, it's very different from there, because here we are just on a curve, so there should be only one degree of freedom. So one variable should be enough to know where we are. So we'll have to express x and y in terms, well, I should say, and z optionally, if there's one, in terms of a single parameter. And that might be just one of the coordinates. If you're told y equals x squared, that's easy. You just substitute y equals x squared and dy equals 2x dx into everything. And you're left with an integral over x. Maybe it will be something in terms of time or in terms of an angle. Some people are having a lot of fun there. Okay, so we express everything in terms of a single parameter, and that will give us, a usual single integral. Any questions about that? Yes?
If you can't parameterize the curves, is it possible to evaluate line integrals?
So if you can't parameterize the curve, then it's really, really hard to evaluate the line integral. Because, well, you might be able to evaluate it numerically into a computer, but most likely, that's the easiest way to describe a curve. So indeed, it could be that in the plane, you have an equation in terms of x and y given by some complicated formulas defining some curve. So then, actually, there are ways you can use basically differentials and constraint partials to figure out what actually the tangent vector to the curve is and so on, but we haven't really seen how to do that. So that would be a really nice topic for tying together the end of the second unit that we discussed last time, constraint partials, with this stuff. But that's not going to be part of our topics. So basically, all the curves that we've seen in this class, there's a way to express the position of the point in terms of a parameter. We haven't seen any curves that are so complicated that you can't do that. Okay. What else? So the other thing we've seen is that there are some special cases of vector fields where we don't actually have to compute this thing, because maybe we know that it's the gradient of some potential function, and then we have a fundamental theorem that gives us a way to compute this without computing it. Okay, so we've seen about gradient fields and path independence. So we've seen that so the thing to check is whether the curl of our vector field is 0. Okay, and remember, in the plane, that's one condition. And x equals my. In 3D, in space, that's actually three conditions, because you have to check all the mixed partials of the various components. So if the curl of f is 0, that tells us we are likely to have a gradient field. Strictly speaking, I should mention, and f is defined in a simply connected region, then F is a gradient field. So that means that we can find a potential function. You can write F as the gradient of F, of little f, for some potential function little f. And we've seen how to find the potential. In fact, we've seen two methods for that. And we've seen them twice. We've seen them once for functions of two variables, once for functions of three variables. They look very much the same. I encourage you to compare your notes for the two side by side to see where they differ. Okay, so where they differ, roughly speaking, the first, well, I never know if it's the first or the second, but one of the two methods was to compute a line integral. So in the plane, what we did is we set up and evaluated a line integral along our favorite path from the origin to a point with coordinates, say x1, y1. And then we had to evaluate the line integral for the work done along this path, and that will give us the value of the potential at that point. If we are doing it with three variables, that method remains very similar. The only difference is now we have to go also up in space to some point x1, y1, z1, and so we actually sum three pieces together. But on each piece, it's the same story, only one variable changes. Here it's only x that changes, here it's only y that changes. On the third one, only z would be changing. That's one possibility. And the other possibility for finding the potential is that we start with the condition that the first component of our vector field should be equal to f sub x for the unknown potential function. So what we do is we integrate with respect to x, and we'll get our potential function, well, up to an integration constant. And that integration constant typically depends on the remaining variables. That might be y, or if we're in space, y and z. And then what we have to do is we have to take the partial of this with respect to y and compare it to what we want it to be, namely the y component of the vector field, and match them to get some information about this guy. And if we have three variables, then there's a third step, because there you still have an unknown function of z that you need to get by comparing the partial with respect to z. Okay? I see a lot of very quiet faces somehow. Well, hopefully that's because you know that stuff. If it's because you're hopelessly confused, then please review a lot before the final. But I really hope that's not the case. Okay, so okay, and so in particular, what we've seen is once we have the potential, then we can use the fundamental theorem of calculus to tell us that if we have a line integral to compute for work along a curve that goes from some point P0 to some point P1, then the line integral for the work done by gradient f is actually going just to be the change in the value of the potential. And in particular, that doesn't depend on how we got from P0 to P1. That's why we say that we have path independence. Okay, next topic. That's flux in plane and space. So flux looks quite different in the plane and in space because in the plane it's just another kind of line integral, while in space it's a surface integral. If you were in four-dimensional space, it would be a triple integral. I mean, in general, you do flux through something that's somehow, a wall that separates regions of space from each other. So, in the plane, the way we do it is we have a curve, C, and we look at its tangent vector, let's call that T, and we rotate it by 90 degrees clockwise. That's our convention to get a unit normal vector that points to the right of the curve as we move along the curve. Okay, so that's our convention for orienting curves, and we're always going to be using that one. Okay, so N equals T rotated 90 degrees clockwise. So in particular, that means that NDS, which will be what we integrate against when we try to compute flux, that will just end up being dy comma negative dx. Okay, so concretely, when we have to evaluate a line integral of f dot n d little s, so geometrically we could try to take the dot product of our field with the normal vector and then sum the length elements along the curve. And in some cases, for example, if you know that the vector field is tangent to the curve, or if the dot product is constant, or things like that, then that might actually give you a very easy answer. But in general, the most efficient way to do it will be to say that, if your vector field has components, I don't know, let's call them P and Q, then that will be just the line integral of pq dot dy comma negative dx, which means negative q dx plus p dy. And from that point onwards, you evaluate it exactly the same way as you would for a work integral. But of course, the geometric meaning is very different. It's the same meaning that we've always seen for flux. It measures how much the vector field goes across the curve. Okay? Now, if we're in space, then you take flux through a surface, not through a curve. And the way it will work is that you have to choose an orientation of the surface, which just means choosing one of the two possible unit normal vectors. And then you will do a surface integral for f dot n ds. So that's the surface area element. So the setup for this surface integral is that first we have to express n and ds in some way. So one possibility is that we can express the normal vector n ds geometrically. That's, for example, what we do when we look at, say, a horizontal plane or a vertical plane or a sphere or a cylinder. Then we have some geometric idea of why the normal vector is what it is. And we have some formula for ds. Or we can use one of the standard formulas. So basically we've seen two formulas that work in fairly general situations. So one of them says, sorry, we need more space for that. So if S is given by an equation z equals some function of xy, then you can just say nds equals minus f sub x minus f sub y 1 dx dy, and I need to rewrite that because I'm running out of space. But while I erase, I would like to point out the most important thing in here. Okay? When I say nds equals blah, blah, blah times dx dy, dx dy is not the same thing as ds at all. Okay? If you make that mistake, you're going to go into trouble the next time that you try to buy real estate in a region with, hills or cliffs or things like that. ds is the area on the slanted surface. Dx dy is the area on the map that shows the xy plane. And these are not the same thing. So in particular, you cannot just take one piece of it and not the other piece, because n, well, actually, let me give you formulas for n and for ds separately, just to convince you. And that way, if you feel that you need them, then you'll have them. So actually, n is minus f sub x minus f sub y, comma 1, but scaled down to unit length. This is not a unit vector. Okay, so it's actually divided by the length of this guy, which is fx squared plus fy squared plus 1. And ds is that same factor times dx dy. And so the two magically, the square roots cancel out when you multiply them together. But it would be completely wrong to, just say, I'll replace nds by minus f sub x minus f sub y and 1, and then I end up again with a ds and I do something else with ds. That's a pretty bad conceptual mistake because it gives you the wrong answer. Another option, more general than that, if we haven't seen how to solve for z, how to express z as a function of x and y, well, maybe we still know some normal vector to the surface. Then there's another formula for nds, which is up to sine n divided by n dot k dx dy. And see, actually, that projection formula works also if you have to project to another coordinate plane. For example, if you want to project to the xz coordinate plane, the relation between nds and dx dz is given by n over n dot j, because j is the direction perpendicular to the xz plane. But I mean, this one is more useful. Okay, so what's a good example of that is, for example, if you have a slanted plane given to you, you can easily find its normal vector. That's just given by the coefficients of x, y, z in the equation. Another situation where that might happen is if your surface is given by an equation of the form g of x, y, z equals 0. If that's the case, then this is a level set of g, and we know how to find a normal vector to the level set, namely the gradient vector is always perpendicular to the level set. So you would take the gradient of g to be your big N. Okay? So now, these are basically all the integrals we've seen how to set up. And now we have a bunch of theorems relating them. Okay, so let me think about how I'm going to organize that. Well, let me try like this. Okay, so this part of the board will be work. This part of the board will be about flux. And the left part of the board will be about things in the plane. The right one will be about things in space. Okay, so what have we seen? Well, we've seen Green's theorem for work. Okay, that doesn't work so well because it's too small. So I'm going to actually use more blackboards to do that. Okay, so this side will be space. This side will be the plane. And we're going to start with theorems about work, and we'll see theorems about flux pretty soon. So we have two theorems about work. In the plane, that's called Green's theorem. In space, that's called Stokes' theorem. Okay, so Green's theorem says if I have a closed curve in the plane going counterclockwise, enclosing entirely some region R, then the line integral along C for the work of F is equal to the double integral over the region inside of the curl of F dA. Concretely, if my components of F are called M and N, that's the line integral of M dx plus N dy is equal to the double integral over R of N sub x minus M sub y dA. So this side here is a usual line integral. This side here is a usual double integral in the plane, and somehow their values end up being magically related. Well, not quite magically. We've actually seen how to prove it, but, you know. Okay. And now the analog of that in space is Stokes' theorem. Stokes says if I have a closed curve in space, okay, so now I have to decide what kind of thing it bounds, and the answer is it will have to bound some surface, but I have a choice of surface. Okay, so I choose my favorite surface bounded by C. Well, I guess I'll just draw it like that. And I have to choose a compatible orientation. So we remember we've seen this right-hand rule for choosing how to orient the surface. I believe in this case, if I take C like that, then the normal vector has to go up. And then it tells me how to compute the work done by F along C. Namely, that becomes the double integral over that surface S of curl F, which I will write as del cross F dot N ds. Okay, so this line integral, it's a usual line integral, but just, you know, if for some reason we don't want to compute it directly, we can actually replace it by a surface integral over any surface bounded by the curve. So it might be that the problem will tell you which surface you have to consider. It might be that you'll be left to choose the simplest possible surface you can think of that's somehow having this curve as its boundary. Okay, and so now remember, curl of a vector field in space is going to be another vector expression. It has three components, and the way you compute it is not by remembering the actual formula, which is really complicated, but by instead computing the cross product between del and F. So you set up the cross product. And of course, it's a highly symbolic cross product. I mean, it's not an actual cross product of actual vectors, but it works the same way. Okay. So both of these formulas basically relate work on a curve with what happens to the curl on the surface that's enclosed by this curve, that's bounded by this curve. And just in this one, you have less freedom of choice because you don't have somehow, you know, a z direction in which you could move your surface. So there's only one possible choice of surface. There's only one thing that's enclosed by this curve in the plane. In both cases, that these things tell you that you can think of curl as measuring how much the field fails to be conservative. See, if your field was conservative, if the curl was 0, then the right-hand side would just be 0. And that would be fortunate because if the curl is 0, then your field is conservative. That means it comes from a potential. That means when you go along a closed curve, well, the change of value of the potential should be 0. I mean, another way to say it is path independence tells you no work. And of course, if you have a vector field that's not a gradient field, then the curl is not necessarily 0, and then you get a more interesting answer. Finally, let's move on to the theorems about flux. So that's green for flux, and that's the divergence theorem. So the flux theorems. So here I say that will be divergence. And here that will be green again. So Green's theorem for flux says if I have a closed curve that goes counterclockwise around some region. So in particular, counterclockwise means that the normal vector will be going out of the region. And then it tells us that the flux out of the region through the curve C, so that will be the line integral of f dot n ds, is equal to the integral over the region inside of div f dA. And remember, the divergence of mn is just mx plus ny. This one here, the divergence theorem, tells you something similar, but now for a region of space bounded by a closed surface. So if you have some region of space and you call its boundary surface S, and you let n be the normal vector that goes, out of the region R. So you orient S outwards. Yeah. Then the flux out of the region through S is going to be the same as the triple integral over the region of divergence f dv. Okay, and remember, the divergence of a vector field with components p, q, r is px plus qy plus rz. So what do these two theorems say? Well, they say essentially the same thing. They say the total flux out of a region is equal to the integral of divergence over whatever's inside. And the reason for that is, again, we've seen for a velocity field, the divergence measures how much things are expanding or how much stuff is being created. It tells you the amount of sources per unit portion of the region. So when you sum that over everything, you get the amount of fluid that's being, the total amount of sources inside here, and that tells us how much stuff has to go out per unit time. That's basically the interpretation. So in a way, I'd be tempted to say that, this table of 4 theorems is somehow the culminating point of 1802. And you do well to remember them. However, I'd like also to point out that these theorems are completely useless if you don't know how to compute any of the integrals that are in there. So all the stuff that was around there before is actually somehow more fundamental. And if you don't know how to compute the double or triple integrals, then this is of little use to you. Okay, so that's the end. I guess I have to wish you happy holidays.